We're going to finish by training our ANN using the MNIST dataset. Training is where the network learns, adjusting internal parameters to minimize errors and improve predictions. We'll understand the training process and how to validate, evaluate, and use the trained model in real-world scenarios. Training involves feeding the model with data, allowing it to make predictions and adjusting its weights according to the errors made. This process is repeated for a number of iterations, or epochs, until the model achieves satisfactory performance. The training data is divided into batches. Each batch passes through the network. After each epoch, the weights are updated. The number of epochs determines how many times the dataset passes through the network. The core of training is backpropagation, in which the errors in prediction are calculated and the model's weights are adjusted to reduce this error using an optimization algorithm such as gradient descent. It's crucial to monitor performance using unseen data, a process known as validation accuracy. The data is split into training, validation, and the test sets. The validation set is used to fine-tune the model's hyperparameters, its initial training parameters, and prevent overfitting, where the model learns the training data too well and struggles with new data, much as when students learn the answers to past exam papers but can't answer a new exam question. Once the validation accuracy stops improving, early stopping can prevent overfitting. During training, the network adjusts its parameters, the weights and the biases. These determine how well the model maps inputs to outputs. The number of trainable parameters depends on the architecture, the number of layers, and the neurons per layer. Monitoring network size is important to avoid overfitting or underfitting. Complex models may fit training data well, but risk overfitting, while simpler models might not capture all of the underlying patterns. Once trained and validated, your model is ready to make predictions on real-world data. With the MNIST dataset, the ANN will predict which digit an unseen handwritten image represents. This process is called inference, using the trained network to classify data on the basis of its learning. However, even a well-trained ANN will make mistakes, just like a person. Understanding these errors is key to improving your model. By examining incorrect predictions, you can identify error patterns and adjust the model, such as by adding more data or refining the network's architecture. A confusion matrix helps analyze errors by showing how often predictions match the correct labels and where the model is tending to go wrong. Our result is pretty strong. For every number not on the diagonal represents incorrect matches. The ultimate test is using an unseen test set held back from training. Accuracy, precision, recall, and the F1 score, which combines precision and recall, provide a detailed picture of model performance. Success here is indicative of the model's ability to generalize to real-world data. Training a neural network is both a science and an art, but it is crucial that you can train, use, and evaluate models effectively to develop robust AI systems.